Our next speaker is Daymo from OpenFOAM, and he's going to talk about 1D and 2D porous media fixed bed reactor simulations using POROUS.
Can everyone hear me? Excellent. All right, thank you very much for attending today and your interest in chemical reaction engineering and OpenFOAM. Let's see. Yeah. Okay. So my colleagues, Akash and Matthias is here in the audience from Karlsruhe Institute of Technology. It's a pretty well-known institution. Me and Lee Tonkovich are from a small business in Gilbert, Arizona. So I've come here, I guess, for the cooler weather, and we have we're just two people, so we really have a need for low-cost engineering solutions so that we can provide technology solutions to our customers. And to that end, we are typically involved with catalytic reactions, surface reactions. A very typical medium for catalytic reactions are catalytic fixed bed reactors or packed bed reactors. These are the workhorse of the chemical process industry. And there are many different tools used to evaluate these types of reactors, including computational fluid dynamics. But OpenFOAM doesn't have, unfortunately, built in some of the key features needed for studying these types of processes, including surface reactions. And if you had a porous media model, there's limited ability for handling packed bed heat transfer. So to enable the analysis of these types of reactors and other surface reaction type reactors, we've collaborated with Professor Olaf Bojman's group at the Karlsruhe Institute of Technology. They have a suite of programs called DETChem. And one of the various programs in the DETChem library is called Duo. It's DETChem and OpenFOAM for coupling OpenFOAM with DETChem. And with that, we can access the detailed surface reaction capabilities within DETChem and provides chemical source terms to OpenFOAM. And we also have access to kinetic theory, transport properties. And so we can, among other things, also model mixed and multi-component diffusion. So continuing the theme of faster simulations, we also are looking for solutions to be able to run our simulations faster, among other things. Optimization is another common theme of this symposium. We in this particular paper that we published a few years ago, we used Dakota coupled with Duo to optimize the catalyst loading and reactor geometry to maximize the production of hydrogen, but also minimize the peak solid temperature. And so we really are looking for a way to simulate packed bed reactors very quickly, and also be able to model the multi-physics of the packed bed reactor. Just in case you aren't familiar with the details of this, usually there are many tubes packed into a reactor. Each of the tubes are packed with catalysts. The catalysts often have pores, and the active material, the catalytic material, is dispersed within the pores. And one way to directly, or more directly, model the multi-physics of a packed bed reactor is to use particle dissolved CFD, where every single particle is gridded or meshed, and the surface chemistry is modeled, and the flow around the particles is calculated. It's very time consuming. This is an 86 particle grid that Matthias and I and some coworkers had worked on with over 1.5 million cells with a couple 100,000 reactive surface spaces. And as you can probably imagine, the calculation times were very slow. In this paper, we published the use of adapting ISAT that's built into OpenFOAM to adapt that for surface reactions. We also worked on a cell agglomeration method for chemical acceleration. And even using ISAT in cell agglomeration, we're seeing for just 86 particles, hundreds of 4 hours of calculation time. And for our simple person business where we don't have access to 400 cores on a daily basis, this was a bit too much. And so we have to look at other continuum modeling approaches. And there's several different approaches for continuum modeling of pack beds. First, there's one type of model where the fluid and solid energy equations are combined into one equation. And there's also an approach of using separate solid and fluid energy equations. Actually, in OpenFOAM, you can model the separate solid and fluid energy equations for the porous media reactor. I think there's a tutorial in the OpenFOAM library. There's a couple of downsides for this approach for fixed bed reactor modeling. First of all, is that there's a transfer resistance between the solid and the fluid, which is a constant which has to be applied ahead of time in the model setup. And also in a fixed bed reactor, typically the reaction is occurring on solid and therefore probably at the solid temperature, not necessarily at fluid temperature. And so we went with the approach of the mixed fluid and solid energy equation. And then even within this approach of a mixed fluid and solid energy equation, there's a couple of other models. There is the alpha W model where the porosity is constant and the superficial velocity is used. And then there's the lambda R model where the actual velocity is used and the porosity varies across the radius of the reactor. So there's pros and cons to every approach, but this presentation focuses on the single fluid and solid energy equation and the alpha W model. All right, so there's a lot of, this is a highly modeled system, and so there are a lot of equations which I'm not going to present in the entire here. I will state this again later. I have posted the source code for this on our GitHub site, and also we plan to publish in one of the proceedings for this where all the equations will be laid out. But here I'll just highlight the key equations. So first, I also want to note that we're using a steady state simulation here. Professor Jacek yesterday mentioned that steady state chemistry is problematic. I think the reason why we have some success here is that we integrate the chemistry over a finite time, even though the simulation is at steady state. And so the key thing to point out on this slide is that we're modeling an effective thermal diffusivity. And the thermal diffusivity is built up by a series of correlations and methods which are found in the literature. And so how does this work? It works pretty well for that case with 86 particles that we had that we ran. We can very easily readily match the performance, the results for dry reforming cases. Dry reforming is the reaction of carbon dioxide and methane to form CO and hydrogen. This was a wedge geometry with about 1,000 cells, and I also want to note that the tube diameter to particle ratio is pretty small. It's on the order of 2, and it's normally not where porous media model is used. So this worked out really well, and we reduced the simulation time from about a day on 400 cores, even with chemistry acceleration, to just anywhere from a few 4 hours to minutes, depending on the chemistry. So this is a very good model to model validation. But what about model to experiment? So we went to the literature and we found a steam methane reforming paper by Wong et al. And this is a 3-step chemistry with Langmuir-Hinshelwood type kinetics. One of the features of DECChem is that we can use an UDF style, user-defined function style for inputting the chemical reaction equations. So it doesn't require programming. It's plus plus. When you change the reaction mechanism, and you quite readily handle a complex mechanism like this. And the temperature gradients are fairly strong. We got a 2D bottle for a media bottle, and you can see that there's over 200 degrees C temperature gradients in this endothermic reactor. And we do a good job of hitting against the experimental data that was presented in the Wong et al. Paper. We also included on this plot results from the commercial code PBR, so 1D simulation, and we matched the 1D commercial code pretty well too. But we can accelerate the calculations even further by going to 1D. And it's fairly easy to set up a 1D grid in OpenFOAM using block mesh. There's just an inlet and outlet. There's two sides which are empty, and set the other two sides to slip down the condition. And if you, with just the basic OpenFOAM package, you can readily simulate adiabatic or fixed temperature isothermal reactors. But what about a non-isothermal, non-adiabatic reactor? For that, we have to consider a additional term you might recall from chemical reaction engineering. The energy balance includes an overall heat transfer coefficient U. At least when I took chemical reaction engineering as an undergraduate, the U value was often given. The details of how the overall heat transfer coefficient is calculated in the fixed bed reactor was really covered, but it's covered in the literature, and we could use again a whole series of correlations in the literature, which I won't entirely go into because it's a lot of equations and a lot of time. But the source code is published, and also and we'll put all the equations into the preceding paper. And this is just an idea of how all the different parameters kind of map together to get the overall heat transfer coefficient. I'm just going to skip over for now for interest of time. And so again, going back to a dry reforming of methane validation case, we do an excellent job of comparing to the commercial PBR 1D code. We should mention that this reaction is a microkinetic mechanism with 6 gas phase species, 13 surface species, 52 surface reactions, and the 1D calculation had just 200 cells. And this runs in a matter of on the order of a minute or so using Duo. Should also note that PBR, which does not handle the axial conduction and diffusion effects, can calculate this case in about 1 or 2 seconds. But I showed a lot of endothermic cases, but you might wonder, what about exothermic cases? And so I also included here partial oxidation of methane case. It also matches the commercial 1D code curve. So in this case, again, it's both microkinetic mechanism with 38 reactions and a number of gas and surface species. So we're seeing a dramatic time reduction for the calculations, which is what we need for reactor design optimization, moving from hundreds or thousands of 4 hours to maybe less than 1 to up to 4 hours for a 2D calculation to 4 seconds to minutes. Now this POROUS media modeling, of course, won't work for every application. There are times when 3D particle resolve CFD is necessary. But in the instances where this highly modeled system will work well for your application, we can churn through many cases in a very short amount of time to help with reactor design optimization. So I did mention this before, that with the source code on our GitHub site. So I think these slides will be available after the presentation. So this link will be available there for you to go to. I have a couple different ways to calculate the transfer effects. One is through a modification of HE Daymo, which used for 3D calculation. I also modified the CHD solver for including the overall calculation. So hopefully you find this to be helpful and useful. And there's an example case, actually a few example cases that are included. This is the 1D calculation comparing against VR. Sometimes in this particular case, if it wasn't as good, I should note that there are a lot of correlation options in the literature for Nusselt number, all the various components that fit into the overall transfer coefficient calculation. And so if the models that I included in the open GitHub repository don't fit for you, hopefully the code structure will allow you to use whatever models you have to fit your data. I'd like to close with one other kind of cool thing that was in our abstract. So in packed-bed reactors, there's often the effect of intra-particle diffusion. There's a couple different ways to actually handle this chemical reaction with mirrors. One is to solve the ineffectiveness factor data. The other is to solve some form of the reaction diffusion equation. There's a bunch of different models for them, but one is shown here. Using effective mixed exhibiting. And one of the really neat things that we have on coupling below with the DEDCAP has what they call a wash code model, which allows for the effectiveness factor or also the reaction diffusion equation to solve to understand the internal reaction. And so for this particular case, I assume that the particle is entirely porous. It is an internal porosity and torque velocity of 1 micron or diameter. And we ran the simulation just to show that indeed in a packed-bed reactor, there are circumstances where you can have substantially worse performance if the internal pore diffusion is and so this is to our knowledge, this is the only CFD option out there with this feature built in. So we're pretty excited about this. So to wrap up, OpenFOAM is excellent. It brings a wonderful toolbox for finite volume calculus, actual production, that's a wide range of numerical options. Really the supporting infrastructure. By coupling with DEDCAP, we have kinetic theory properties and microkinetic surface reaction mechanism capabilities, intraparticle diffusion models, and what also is really kind of neat as both a developer and a user is to be able to import or write the reaction model out in the UDF format. It's very straightforward and easy to program and make changes. And so I hope that we've been able to show that for some applications moving from 3D to 1D, oftentimes adequately modeled particular reactor performance or fixed-bed reactor performance with dramatic time reduction. We've upgraded the porous media modeling capability of packed-bed reactors to include the transfer effects from OpenFOAM. We did this by combining the fluid and solid energy balance and introducing an effective conductivity overall transfer. And I think that concludes my talk. I'd like to thank my co-workers, the ideas of the project for their contributions and detailed discussions and even just listening to me on some days. Thank you very much for your time.
Have a few minutes for questions for Eric. Yeah, what? Yeah, so the alpha W model is an approach where the porosity
it's a packed bed reactor, right? So the porosity is constant. It's called the alpha W model because the boundary, the boundary condition needs to be a heat flux boundary condition, hence the alpha. And the simplification is that the porosity is constant, the superficial velocity, a constant superficial velocity can be applied, well, it's constant across the diameter change, the temperature, but a constant radial velocity is used. But you do have less accuracy of the thermal modeling at the wall. There was a figure in the presentation that shows the accuracy of the two different models approaching the wall. Purchase the time, we'll look at that offline. The other competing model, lambda R model, is more complicated to set up because it has porosity that varies across the diameter of the reactor. The actual velocity is used, for example, the superficial velocity divided by the porosity. It's much higher, but a fixed temperature boundary. And if I didn't answer your question, I'd be happy to speak to you in detail about this. Right. Yeah, so great question. So I collaborate with KIT and Matthias. I mean, kind of the general idea is that if there's an area that either A, we have business or C business in, or B, just personally interests me. We've done a lot of work with KIT on just topics I just find to be fun. Karlsruhe Institute of Technology at Matthias is. I'd be happy to talk at the break. I'm very interested in collaborating and learning and continuing this adventure.
Any more questions?
There's a lot of different diffusion options that we have, including multi-component diffusion and mixture average diffusion. Certainly there is a modest cost over using like a Lewis number of one type of approach, which is built into more resource number one, which is built into different versions of OpenFOAM. Multi-component diffusion is definitely more visible in the time increase. For the smaller type reactor simulations that I run, the time increase for mixture average diffusion, like a Fickian diffusion model, is negligible. It's very fast to calculate the diffusion coefficients. Parametric optimization. Sorry, parametric optimization. Oh, parametric perturbation. Oh, interesting. No, I did a brute force approach of setting minimum and maximum values of channel dimensions and catalyst thickness, which we did through a FCAT geo parameter. And we turned on the genetic algorithm and churned. I ran cases pretty quickly and popped out, that the data that we're able to populate that graph. I do a lot of genetic fitting, and so I use a lot of genetic algorithms with Dakota company to depth chem tool and also duo, but I haven't tried, if I understood correctly, I haven't done a perturbation type of stuff.
Okay, let's thank the speaker again. Thank you very much.